Okay, so we have a blank slate. So I did the video on binary and how that's used to actually set the channels on your radio. And that's what most radios use, with the exception of really modern radios that have programmable PLL ICs. But back in the day, there were two popular kinds. And it almost kind of depended on what manufacturer you got your radio from. If it was a Uniden, it had a UPD 858 in it, and if it was a Cybernet, it had a PLL 02A. The last one I showed was the PLL 0 or 02A, which uses regular binary encoding. So the one that was used in the Uniden chassis, which was the UPD 858, uses what is called BCD. So BCD stands for Binary Counting Decimal. Now, if you haven't watched that first video, you're going to have to watch it. I'm not going to completely cover binary again. So you need to understand binary if you want to understand BCD, because it is binary counting, just as the name says, decimal. And that's what's kind of different and kind of weird with BCD, is it uses both. So, and I've got a channel or a truth table, just like I did for the PLL02A. I have the truth table I've made up. Like I said, I make those up for all PLLs, well, at least very popular ones. I've got one here for the UPD 858 as well. So if we just get that out of the way here, I'll just really quick cover the different counting systems again. So when you went to grade school, your normal math that you learned and your normal way of counting was what they call base 10. So that uses 10 different characters, and this just happens to be what someone at some point in the past in ancient history, I guess you could say, came up with for numbers. They're just pictures or symbols, but that represents the 10 characters that are needed to make up pretty much any number you can think of. So if you wanted to write 456, well, that's exactly what you would write, 456. But that's the decimal system. If you remember, binary is a base 2 system, so it only has two characters, 0 and 1. And the reason that we use binary instead of decimal when it comes to microprocessors and computers, and it doesn't even need to be a computer, it can be just simple CMOS TTL style ICs, but the reason we use binary is this is something that is easily, how should I say this, accepted by an integrated circuit, because there's only two states, and you can represent those two states as they do. 0 is a low or a ground potential, and you'll see 1 is a high, or that'll be your voltage. And that depends on the IC. They can operate at some different voltages, but that's going to be your high, is the 1. So, like I said, BCD stands for Binary Coded Decimal. So it is binary, but it's coded into a decimal system. So it is a little confusing. Don't worry, it's not that bad. If you understood binary, you won't have any problem with this. Again, there are some things, if you remember from the video on binary, there are a few things that are backwards. There are some things that aren't backwards with BCD. There are some things that's actually a little bit easier. Also, trying to get channels kind of depends where your channel 1 or 40 falls at if you're trying to get expanded channels, but it can be a little bit easier to actually get with BCD because of the way it's doing this in a binary and decimal way. So as before, like I say, it says this uses binary, but it only uses 4 of the possibilities. So this uses, some people refer to this as the 8421 code. Now, in the case of CB radios, yeah, everything's backwards usually, so it's actually, I guess you could say, the it's 8421 or the 1248 system, but these, just as in binary, this is the weight. So it's going to be a weight of 1, a weight of 2, a weight of 4, and a weight of 8. So, 2 plus 1 is 3, 4 plus 1 is 5, 8 plus 2 is 10, which is, by the way, and we'll get to it later, that's not allowed in BCD. It's one of those weird idiosyncrasies. So I have here written across the top here, I have weight. So this But you'll also notice there are 3 columns. So we're going to be turning basically from 1, 2, and 3-digit decimal numbers. So that would be like a 1 or a 15 or 136. We're going to turn, some random numbers like that into BCD. But unlike binary, if you remember, when we did binary, the weight just continues to increase. So you have a weight of 1, 2, 4, 8, 16, 32, 64, 128, 256, and if the numbers got big enough that not for CBPLLs, but in normal computers, you can get much bigger than that. You can get pins that have a weight higher than 256. But notice it's times 2. 1 times 2 is 2, times 2 is 4, times 2 is 8, and so on. It just keeps going up. BCD only uses those 4 digits, 4821. So to make larger numbers, more than a single digit, they actually have a column. So you'll see here I have ones, tens, and then hundreds column. So that's the way it counts. Again, the way you'll normally see BCD, just like binary, it's going to be written most significant digit to least significant digit. So, hundreds are more significant than tens or ones, so you're usually going to have your highest digit here, then your second highest, and then the lowest digit's going to be over here. And again, when you look at the actual binary numbers, they're going to be 8421 from most significant to least significant. So if we wanted to encode the decimal, so any number you see over here is going to be a decimal number, which are the numbers you're used to using. We wanted to convert that into BCD, that would be 0001. Because remember, now this is only a single digit, so we only need the ones column. And then we need a weight of 1, so that's all it would be, 0001. You get to the number 2, then you put the 1 in the 2's column, because that's what you need, is a weight of 2. We don't need the 8, the 4, or the 1, so it's a 0. 3 is 2 plus 1, so that's why there's a 1 in the 2 column and the 1 column. So just like with binary. Same thing for 5, there's a 1 in the 4 column and a 1 in the 1 column. 4 plus 1 is 5. Now when you get out to a second digit, so each digit in the decimal style number, okay, is going to add an entire column of 4 binary bits, okay, the 8, the 4, the 2, and the 1 for every single digit. So ones, tens, hundreds, and then this could just keep going out. You get to the thousands, the 10,000s, the 100,000s, the millions. But you're probably seeing the problem with BCD already. If you get really big numbers, well, the BCD number doesn't get big. It gets huge. Binary gets big. BCD gets even bigger, even bigger still, because of that using 4 columns for every single column of the normal decimal digit. But once we get out to 10, so just look at it that way. What's the first digit the first column in that digit is a 1, so that's what you need, is a 1. The second digit is a 0, so it's all zeros here. So we have a 1 in the tens column, so that's a 10. So that's what this is. That's what this means by tens and hundreds column. If you whatever you specify in binary in that tens column is going to be its weight. So if it was a 1 in the 4 column here, that would mean a 40. So you come down to 20. We're going to put the 1 in the 2's column. Again, the second digit is a 0, so we have all zeros in the 1's column. You get out to something like 37. So we're going to have a 1 in the 2 and the 1 column. 2 plus 1 is 3, times, because it's the tens column, would make it a 30. And then 0, 1, 1, 1, because 4 plus 2 plus 1 equals 7. So that's 37. And again, you can see we come out one more decimal place. In the decimal number out to the hundreds position, we have to add yet another column of 4 numbers. And you can see, again, 1, 0, 0, so we'd have 1 in the hundreds column, so that's 100. And then zeros in all of the tens and the ones columns, because we don't need anything there. And then just some other random number like 115 is 1, which is a hundreds, 1 in the tens position, and then 4 plus 1 is 5 in the ones column, so 115. Now, the largest number you can write in BCD with these 3 columns, or the largest number you can write actually in any column, is a 9. You can either have a 0, which just like here we have all zeros, just like our decimal number up here, we have 0 through 9. So that's all that we can count. But do you notice a problem here? Or it's not so much a problem, but do you see something kind of strange? Well, if 999 is the largest number you can write, or just a 9 is the largest number you can write in decimal in any one of these columns, why are there zeros here? Well, if you add 8 plus 4, that's 12. 12 plus 2 is 14, plus 1 is 15. And then, if you had all zeros here, well, that's another digit, so that's actually 16. So you can actually get 16 digits out of BCD the way they count here. But obviously, you can't go sticking 2 digits in a single column. So those are commonly referred to as the forbidden numbers. So what are the forbidden numbers? It's pretty simple. It's anything above 9. So you cannot have a 10, 11, 12, 13, 14, 15, and this is what those are, of course, in BCD. So, 1, 0, 1, 0, which would be 8 plus 2, which is 10, 8 plus 2 plus 1, 11, 8 plus 4 is 12, 8 plus 4 plus 1 is 13, 8 plus 4 plus 2 is 14, and then 8 plus 4 plus 2 plus 1 is 15. But none of those are allowed because we can't have a BCD number that comes up to more than a single digit. Just something to keep in mind. So now, when it comes to actually doing, if you're like doing channel modifications, again, just like I had said with binary, probably the easiest way to learn how to do this is to write it. Just like I showed with, the PLL02A chart that I have here, where this was all handwritten out. At some point in the past, I did the same thing for the UPD858 and several other PLLs. But you'll notice that the highest encode, so just like I did in the video for the PLL02A, I have a weight, pin ID, and a pin number column, and then the encode, which is the actual decimal number. But you'll notice with the PLL02A, the highest encode is 511. With the UPD858, the highest number is 399. And if you look in service manuals, just like with the PLL02A, you're going to find things are not written as you're normally going to see them. Like I say, BCD is normally written most significant to least significant digit in both the weight of the columns and how the binary numbers are actually represented here, 8421, from most significant to least significant, and then the same thing for the weight of the columns, hundreds, tens, ones, so most significant to least significant column. Again, CB radio, well, they just have to screw with us, so everything's backwards, just like with the PLL02A. So when you look in a service manual, and actually, I think I still have one out here. Let's see here, President, yeah, that one should have it in. Just working on one of these. So yes, President Madison, and there it is, there's the truth chart. So, if you look at the truth chart here, and I have written in, ones, tens, I got a little squiggly line there, but yeah, so these are the ones, this is the tens column, and then here's the hundreds column. Now, just like with the PLL02A, very frequently when you look at those in a service manual, they will not have all of the program pins written down for the truth table. That's because very frequently one or more pins will stay at a continuous state through all 40 channels. The UPD858 in this example, the early version President Madison, is the same way. So I had written that over here. Pin 22 normally is at a state of 0 through all 40 channels. It doesn't change. Okay, and then that's an encode of 91, so if you do the math over here, this is a 91 for channel 1 and 135 for channel 40. Now, did you notice something there? If you remember when we did the PLL02A, how I said pretty much everything's backwards on that one, this one is not so much. Notice that as the channels increase, actually let's just show it on this chart, so as your channels increase, let's see, get to 2, or no, 91, there we go. So as your channels, so on here I have written, from channel 20 to channel 40, as your channels increase, so does the decimal number, and likewise, the BCD number increases. The PLL02A, if you remember, as the channel numbers increased, the encode and the binary number on a PLL02A decreased. They were going in opposite directions. Luckily, the UPD858, they at least got that right. The channels increase, the decimal number, and likewise the BCD number increase. Another thing that's backwards on the PLL02A and is in the correct order on the UPD858 is the pin ID numbers. So again, the pin, I'm just referring to the pin ID. When you look on a data sheet, it'll tell you, this is the VSS pin, or your program pin 0, pin 1. Those are what the pin is called. And then you have the pin number, which is the actual physical pin on the IC. But notice they both increase here. The PLL02A, if we pull that chart back out, you can see, program pin P0 is a 15. As this number increases to P1, this decreases to 14, so they're backwards. The BCD, or the UPD858, that's another thing they got right. As the name of the pin increases from P0 to 1, 2, 3, 4, 5, 6, all the way up to P9, so does the actual pin number. The physical pin number on the IC actually increases as well, from 13 to 22. So yeah, they got a few things right. So like I say, pretty much everything else in that other video holds for this one. If you're doing channel modifications, same exact thing. You're basically, all you're doing is cutting a trace, you're installing a resistor to bridge across that trace, and then you're going to supply either a ground or a voltage to it to, I don't want to say trick, but you're sending a different logic level to the IC than what your channel selector is actually doing. Because that's all you're doing. You're just basically cutting the line, bridging it with a resistor. That resistor is basically, in a nutshell, preventing smoke from coming out of your radio, because you may have the channel selector supplying a ground to the PLL, and with the modification that you want to do, well, you may want to supply a 1, which is a voltage. Well, you can't apply voltage and ground to the exact same pin and not expect magic smoke to come out. That's why you add the resistor in between there, and then that way when this pin's at a ground state, when you apply that voltage over here, you have that several K resistor, you have several thousand ohms of resistance in between there that are isolating those two pins from coming in, those two different logic levels, the 0 and the 1, from interacting with each other. But yeah, so channel, like I say, channel modifications done the exact same way if you're doing it the old school way with toggle switches. Of course, you can do it more modern ways. You can use a microprocessor controlled. You could use an Arduino or any of the other development boards out there to make up your own little channel boards. And that's all you're doing. You're just sending this code, the proper pin programming, to the PLL chip to get those channels. Now, one of the nice things if you're doing it with a toggle switch on the UPD858 is it's usually fairly easy to get channels in blocks of 10 channels at a time. Unlike the PLL02A, where, yeah, everything kind of, the columns just keep increasing or decreasing the farther out you get. Remember, the highest binary number you can have on the BCD type system is a 9. So there's a 1's columns, a 10's columns, and a 100's. Well, that basically equates to in single-digit channel numbers, double-digit channel numbers, and triple-digit. So, this is like channel 1. So, you have channel 1 here, has a BCD number, or the encode of 91, and then this is the BCD number for it. But if you look at this, now remember, again, something to confuse you, it has nothing to do so much with the PLLs. It was just the way the FCC had the channel band set up back in the 23 channel days. There's a channel missing between 3, 4, 7, 8, 11, 12, 15, 16, and 19 and 20. So there's a People commonly refer to those as 3A, 7A, 11A, 15A, and 19A. But for every 10 channels that you go, or 10 spaces, because even though you've gone 10 CB channels here, remember you've skipped over 2 channels, because there's a total of 5 missing channels due to those skips from the old 23 channel days. But you can see what happens here. If you look in the tens column, okay, so remember, written backwards from the way you normally write it, truth tables, like in the service manual over here, are usually written backwards from the way you'd normally see it. So they have least significant to most significant in the column weights, and then they also have the binary in each one of those weight columns is also written least significant to most significant. Now, one thing to note is in the hundreds column, there are only 2 digits, a 1 and a 2, where in the ones and the tens position you have 1, 2, 4, and 8. The reason they did that is, well, they didn't need more than that. Remember, the highest possibility on this PLL is 399. So they didn't need to go any higher than that. They didn't need a 400s position, because that's basically what this is. This is the ones column in the hundred, or the 1 in the hundreds column, so this is 100. If you put a 1 in this column, that's a 2, which is 200. The next column would be 4, which would be 400. So, and then 4 plus 2 is 6 plus 1 is 7. They didn't need 799, so yeah, they went with the 399 as their maximum. So, and actually that's, as you can see, right here, the highest channel, 399, is 1, 1 for, 2 plus 1 is 3 in the hundreds column, so that's your 3. Then you have the tens column here, we have an 8 plus 1 is 9 for the tens column, and then an 8 plus 1 is 9 in the ones column, and that's our 9 for 399. Remember, that can't go up above that. That's the largest number you'll see written in binary in each of these weight columns, because anything higher than that is our forbidden numbers. But like I say, you can see how it's fairly easy to jump 10 channels. Unlike this one, where you go 1, 2, 4, 8, but you also have a 16, a 32, 64, 128, 256 column. This one, every time you get 10 channels or 10 frequencies, you're going to go up. This column here is going to go up by a weight of 1 to add another 10 to the count. So, if you go from 380, you can see we have in the tens column, right here we have a 1, 0, 0, 0. So that's an 8 for the 8 in 80. And when you get up to 90, the only thing that changes is that we need to add 1, so it's 8 plus 1 is 9. And then when we get to the next one, well, the next one up from that's going to be, well, actually, there's not going to be anything up from that, because I'm at the top of the chart. We can't go higher than 399. So, if we were to start down here somewhere lower, like at 360, so we would have, camera mounts in my way here. I need to get my head down, see where the column is. So you can see we have a 0 in the 8, we have a 1 in the 4s column, and a 1 in the 2s column. So that's 6 for this, 60. And then if we go up to 70, you can see the only thing that changed here was this column here that was a 0. We needed to increase that weight from a 6 to a 7, so we added 1 to the count. So that's usually all you have to do to get the additional, an additional 10 channels, is usually you're just adding a 1 in the tens column. So, if it was all zeros to start, let's see, 300. So, let's say if we started at 300, because we have a 0 in the tens column, so you can see it's 0, 0, 0, 0. If we wanted to jump up 10 channels from that, all we would have to do is add a 1 in this column. And if we come over, we can see that. We get to 310, on 309, it goes from a 0 to a 1. So it's now 310. And that's all you need to do, is just change the state of the tens pins to get blocks of 10 channels. So that makes a little bit more sense. It doesn't jump around. It can tend to get a little jumpy on the PLL02A just because it's just an ever-increasing binary weight. It doesn't get to 10 and then reset, which is basically what you can think about this as doing. It's basically what it's doing. It goes, the ones column counts from 0 to 9 and then resets. And when it resets, you're going up you're going to add 1 in the tens column. Counts from 0 to 9 in the ones column again, and then when you go 1 digit higher, this column is going to reset. It's going to add another 1 in the tens column. And likewise, if you're in the tens column, you have 80s, it's going to count up. This one will count from 0 to 9, then jump up. This column will jump to 90s. This column will count from 0 to 9, then up 1 more digit. This column would switch from 90s to the hundreds. So it would go back to all zeros, and then you'd have a 1 in the hundreds column to make a 100 position. But like I say, you can easily change 100, 10, or 1 at a time. There is no 1, 10, and 100 column on a PLL02A or any PLL that has normal binary encoding. So I hope that explains it. Like I say, everything else is pretty much the same as a BCD, how you do the modifications, and a lot of it's the same. This uses binary, but it only uses 4 digits, 1, 2, 4, 8. So if you learn the normal binary, this one should be easy to pick up. That's all you need to learn, is that you're only using the 8421, or in the case of the way CB radios, it's written out, the 1248 code, but it's just in columns, ones, tens, hundreds. So I hope that explained that. Like I said, I thought I'd do a follow-up on that because I don't want somebody to go working on a UPD 858, go pulling the service manual out, looking at the pins. They're trying to do binary, counting, which is ever increasing in weight columns, and that's not how the UPD 858 works. It works in this kind of a weird system. Now, something else to remember is very common, your 7-segment displays, you'll have BCD counters. There's 4 7-segment displays. That's very common, so it's actually handy to learn how BCD works, because BCD is used with some other systems. It's kind of a go-between. This is fully computer. It's nothing but ones and zeros. This is a hybrid. It's binary, ones and zeros, but it's also decimal, ones, tens, hundreds. And then of course you have your normal decimal, which is just writing the number out like this, is a full decimal number. So BCD kind of falls in between, and that's why it's actually used for some things. But like I say, it's handy to learn, especially if you're going to be doing any channel modifications. This is, some PLLs use this BCD encoding, so just another tool to add to your toolbox.